Thanks for inviting me, guys. So today's talk is going to be on basically the latest work on people using AI, machine learning to optimize database systems. So this is something I've been working on since I started at CMU over a decade ago. And the problem actually goes far back to the 1970s when people started building the first database systems. Uh, so, and like everything related to AI, progress has really accelerated in the last 2 years. So I'm going to sort of go through what what led up to where we are today and how things like LLMs are pushing the next generation of automatic tuning in database systems. Right. So first, we got to do some background on like what are we actually going to tune in databases. So for this audience here, it should not be a surprise to say databases are really hard to optimize and maintain in production environments. So there's a bunch of tools that people have developed over the years to target different aspects of database systems to try to optimize them for whatever the workload or operating environment that they're running in. So one of the most common things that people optimize are system knobs. So these are the runtime parameters the database system exposes to you to change the runtime behavior of the database system, like buffer pool sizes, caching policies, log file sizes, and so forth. Right? The other thing you can tune is the physical design of a database system. I know we just had the Dragonfly talk, but I don't think they support SQL with the relational model. But in most databases are going to be the relational model. And so in that environment, you need indexes. You need to define things at the lower physical level, what the tables are going to look like in order to get the best performance. Then there's query options or the query tuning. So this is the parameters you can specify to the database system on how to the join order for queries, what indexes to use, and so forth. In some cases, there are tools now that can take a SQL query and rewrite it into a new SQL query that is designed in such a way that the optimizer will have a better chance at generating a more efficient query plan. But these are pretty rare. And the last one's going to be what I'll call loosely lifecycle management tools. So these are trying to deal with not so much like how to make this one query go faster or how to make the, what index to use and so forth, but rather how to deal with the long-term maintenance of a database system, right? So simple things like how do I scale up and scale down my instance size? How do I handle migrations from the application developers that put out new features? When should I deploy them? How should I deploy them? And then the big struggle for a lot of people is then how to upgrade or even migrate to a new database system. So again, it goes without saying that there's a lot of things you have to consider if you want to maintain a database system. It's a beautiful piece of software. It needs a lot of work. It's like a small child, right? So I'm going to go through all of these different tools that try to solve this problem, except for this last one here. This is actually something there isn't very good tools out there. And no matter how great sophisticated machine learning is getting, there isn't really anything today. But this is something that we're looking in right now. Like Amazon and Microsoft have basic calculators to try to tell you whether you should upgrade or not, but nothing is really helping people in the real world. So I want to go through, for this talk, I'm going to go through the sort of what I call the past, present, the frontier, and the future of using machine learning and AI to automatically optimize database systems. And as I said, this is a really old problem. It goes back to the 1970s when people were building the first relational database systems. Like my PhD advisor's, his advisor's advisor wrote like one of the first papers on automatically picking indexes in the 1970s, right? So if you want to tune out for the rest of this talk, because you only really care about LLMs, we'll get to that part here. So give me 15 minutes, we'll get there. But like I said, there's an old problem, and people have been doing this for a long time. So the past really is leading up to like 2020, right? And then when the LLMs come along, that's when things change a lot. So I was trying to think of like what imagery or iconography I could use to demonstrate this progress over the years. And I was trying to think of like what celebrity, what person could I show in these bubbles to show it has the age over time. And I was thinking, what celebrity has been sort of in the public space for the last 30-something years, 40 years, that has aged gracefully, and we can kind of show nice pictures as they go along. So my first thought was, Tom Cruise, right? He's a good-looking dude, and he's done a lot of movies for a long time. But then turns out I forgot that his daughter now goes to Carnegie Mellon, and they explicitly told us we're not allowed to talk about her in any public setting. We can't email her. She's not taking my database class, so we'll have to ignore that. But let's go with Denzel Washington, because that was what we started off with ChatGPT in the beginning of the video. So we'll just go with Denzel's movie career as we go along. All right, so the earliest database tuning tools are actually basically how people were building tuning tools today. So you have some input, like the workload I'm going to run, an objective function, or the thing I want to optimize for, like latency or performance or cost. And then sometimes you also have environment information, like how many CPU cores I have, how much memory I have. And then you're going to feed that in some kind of tuning agent. I'm not defining what that is or how it's going to compute, crunch on that data, but it's going to do something. And then it's going to generate a new configuration that you didn't apply to the database system. And the more sophisticated ones can take feedback from the changes that they make or recommend, and then reincorporate that in their internal algorithms or the models to make better decisions in the future. So this chart right here, again, whether it's using LLMs or your off-the-shelf branch-bound search algorithm, they all pretty much work the same way. So how good are they? So if you take Postgres 16 out of the box and you run the join order benchmark on it, if you don't do any tuning, like you take whatever the Ubuntu configuration you get when you install it through the OS, you'll get, for this particular workload, you can complete in about 400 seconds, right? Not that great. If you tune just the knobs or just the indexes or just queries using these sort of state-of-the-art algorithms today, right, you can get a pretty significant improvement. So in this example here, I'm only tuning the knobs and leaving the indexes and queries alone, or I'm only tuning the indexes and leaving the other two alone, and so forth, right? pgtune is the one that everyone uses. It's basically a bunch of if-then-else statements. It's not using machine learning. It's not using AI. It does a reasonably good job. But the DTA and the auto-stew algorithms, those are machine learning based, and they're doing something more sophisticated. All right, so it's kind of obvious here that, okay, well, I've had 3 things I want to tune, but in this example, I'm only tuning one of them at a time. Well, can we tune all of them? So the way you basically would handle this is to use what are called sequential tuning. And the idea is you're going to choose whatever tuning algorithm you want to use, start with, tune that in your database system, then take whatever the output is that came out from the previous tuning algorithm, apply it to the next one, and apply it to the next one, and then so forth, you're done, right? So we could tune the knobs, followed by the indexes, followed by the queries, right? So it turns out, though, when we run analysis on this, right, because there's all possible, there's 3 choices, so you have to look at all possible combinations of those 3 choices, with the ordering of which you tune first, it actually can make a pretty big, significant difference in performance. And I can't say things, oh, you should always tune indexes first, then tune knobs, then tune queries. It turns out when we run that experiment on a bunch of different workloads, that the order changes per workload. So you kind of like left up to like trial and error to figure out how to tune these things. So we go back to this graph here. We take the same benchmark we had before. And what I'm going to show you is the sequential tuning scheme that is the worst one, and then the best one. So it turns out if you tune the queries, followed by the knobs, followed by the indexes, that performs the worst in Postgres for this workload. But if you do knobs, indexes, and queries first, that does the better, right? So it goes without saying, it's not surprising that we're going to do better than we did before if you only tune one of these things. But of course, we'll see in a second, we can do even better if we can think about these things in a more sophisticated way rather than just flipping a coin or picking one after another. So this is basically, again, the last 30, 40 years of how these automatic database tuning tools have worked, right? They only look at sort of one thing at a time, and people try to cobble them together to try to do multiple things together, but it's really just, again, just doing one after another. All right, so let's now jump now to what I call the present. So this is 2020 up to 2024, right? So the last 4 years. And there's a bunch of research, a bunch of work looking into how to solve this sequential tuning problem by allowing to do multiple rounds. So the idea is that you have some kind of coordination framework that can say, all right, well, I know I have these different agents that can tune these different parts of my database system. So instead of just me trying one after another, I'm going to have an internal model that can try to figure out which of these tuning tools or tuning agents should they try out at every given step. So you do something really simple, like I'll tune the indexes, followed by the knobs, and followed by the tuning the queries. But then the coordinator can say, well, I think I'm going to get more benefit if I try again to tune the knobs, given that I've tuned all these other things, right? Again, there's different scheduling policies, how you explore these things. You can just randomly click through or have a separate idea, like I'm going to get more benefit from indexes, right? It's sort of tied to the objective function that we talked about before. So they're the leading framework in this space is actually from Alibaba, and it's a framework called Unitune. And so they're going to be doing using roughly the same off-the-shelf algorithms for tuning the single category of parts of the system. they're not really going to do a good job at tuning queries because they're relying on calcite to do rewriting. And so if you just do that, you're actually going to end up doing worse than sequential tuning because the time budget is spent trying out things that actually turned out not to be beneficial. Okay. Great. Part of the problem that's going on here is that, and this will be a recurring theme in the rest of the stuff we talk about, is that the database system has its own internal model in the query optimizer about how it thinks it should use indexes or tune queries and so forth. And so a tool like this has to build its own model to then try to mimic what it thinks the optimizer is going to do. And in the case of Unitune, it doesn't do a very good job here. So instead of having these multiple agents try to figure things out, because the agents don't know about each other, and so you may end up with sort of a prisoner's dilemma issue where one agent say, hey, I really want to tune indexes, and this is the thing I want to be tuned. I want these indexes. But it may actually be better off for the query tuner if it had another set of indexes, because then it could find the true global optimum, right, rather than getting stuck on a global minimum. So what you really want to be able to do is sort of throw all the choices that you have to tune your database into a giant pot, swish it around, and then try to figure out from all those possible choices what the optimal configuration actually should be. Because then you don't get stuck in one of these local minimums that you can never break out of. So a naive thing to do would just take all my choices, so all my knobs, all my possible indexes, all my possible query tunes, throw them together and try to come up with the optimal algorithm to generate these things. Right, the problem, of course, as you can expect, this is an NP-complete problem, or NP-hard. Just solving one of these, like picking the right index is NP-hard. So now you're trying to pick the best knobs and best query plans. It gets even worse, right? It's not NP-complete, but it's still NP-hard. So why is this so difficult? Why is this a bad idea? Well, of course, again, obviously, there's going to be a lot of configuration choices we could have. And so the algorithm spend a lot of time crunching on things before it actually starts converging, coming up with good results. The challenge also, too, is that the problem space is actually really sparse, meaning the number of possible configurations we could have is massive, but the number possible of valid configurations or helpful configurations is actually very, very low, right? Like my table has 1,000 columns, building an index on all those 1,000 columns is probably going to be a bad idea. And so you kind of have to have some sort of tuning or guidance, domain knowledge, if you will, in these algorithms in order to make this actually work. The other big observation that we had is that many of these choices that we can use, or many of these things we could use to optimize the database system, are actually redundant, are very similar to each other. And therefore, we don't need to look at every possible discrete choice. If we can rely on understanding how certain configurations make a difference, we can then infer from that like how ones that are very similar to it will also help or not. So what do I mean by that? So say I can tune the amount of memory I'm going to use my buffer pool manager, right? Well, setting the buffer pool manager to 32 gigs is about roughly do the same as setting it to like 33 gigs. Like in Postgres, for example, you can set the shared buffer size to any arbitrary number between 0 and whatever, 64 bits you can go up to. But the incremental jumps from like 1 megabyte at a time is not going to make a huge, huge difference. But all of these tuning algorithms look at these all discrete choices and has to consider all of them and doesn't know things that are close to each other are going to be the same. Likewise, if I have an index on A, it's probably going to be about the same as on the index on AB, right? Of course, we need to know that index on A is not the same as index on BA in many systems. So you have to be aware of where the structural similarities are actually correct and where they're not. And likewise, similar to the knobs for the system, the knobs you could set for queries roughly behave the same way. Like setting that amount of hash memory I'm going to use to do a join from 1.1 megabyte to 1.1 megabyte is not going to make a difference. So instead, what you really want to do is be able to infer that you're going to get some benefit or degradation in performance from these similar actions without having to try them all. And that's going to significantly reduce the complexity of the search space. So I'm not going to go into the details of the algorithm that we developed last year, but the paper is public. We're happy to talk about it afterwards. But it's basically going to be a reinforcement learning algorithm that's going to use ideas from LLMs that allow us to represent a configuration of a database system that normally would be in a high-dimensional space down to a smaller embedding, a smaller vector, and that's going to allow us to identify the similarity we could see from these different choices. And of course, like any reinforcement learning algorithm, there's a trade-off between exploring more solutions of the unknown space versus exploiting what you know about already. And like any other algorithm, this isn't magic. It can take a while to try to figure out what the right configuration is. So let's go to that same benchmark now. And now if we use the algorithm that I talked about before that can exploit that similarity, we can see that we can get a pretty significant improvement in performance, right? About 2x better than Unitune, or 2x better than the other choices we have there, right? So this seems fantastic, right? Problem solved? Well, not quite. So what I've shown here is we've essentially had to train a local-only model that is hyper-specific to one single database instance. That means the number of CPUs, what the schema looks like, what the workload looks like, and so forth. And that if someone comes along with a new database system, we essentially have to retrain our model from scratch, which can be expensive because it's not like a robot where you can build a simulator, or the self-driving car people that build a simulator that can pretend to be driving around to collect data, right? Building a simulator for a database system is just as hard as building a database system, so no one would ever actually do it. You actually run the real queries and collect the telemetry. So what we want to be able to do is leverage what I'll call the world collective intelligence of people that have tuned other databases, and then apply that to our learning algorithm so that we have to retrain from scratch all over again. What does that sound like? LLM. So that's why this is the frontier. So this is what people have been doing in the last 2 years. So there's been a lot of work done on tuning all these different aspects of the database system using LLMs. I'm just showing you a smattering of some of the latest research in the space, although Supabase and Tembo's work is not academic. And the Supabase one, as far as I know, is pretty limited. It's just calling ChatGPT, it's nothing fancy. So I'm going to focus on the knob tuning stuff for now, and then I'll talk a little bit about this upgrade advisor prototype that we built, again, trying to rely on LLMs to tell you when you should upgrade Postgres or not. So for design tuning, the idea is that we're going to rely on LLM's ability to spit out useful information and answer questions. And there's a bunch of documentation on websites or Stack Exchange or people discussing, hey, my database was slow. Someone makes a recommendation about how to tune things, and the LLM has sucked that up and it can regurgitate that for you. So again, instead of having to train a custom model, as I did with the one I showed before, we're just going to rely on LLMs to hope that they've seen enough workloads out there or enough information out there and be able to generate useful responses. And the challenge is going to be, how do we actually do the prompting, right? You can do it on a per query basis and say, here's my one query, make this go faster. Or you can do it across the entire workload. Of course, now the challenge is, how do you get that into the prompt? The jury's still out what the right way to do this is. So this is not my own work. This is actually work done by Emmanuel Trammell at Cornell. He's sort of somebody who's been at the leading edge in this space. So they have a paper in Sigma this year, which is the top database conference. Basically shows that you can generate a prompt about, hey, I want to tune my database, and then you feed that into an LLM. You could fine-tune it if you want, but I don't think they did. And then it'll spit out some recommendations that you could then apply. And it's basically plain text that you could then apply to the system to optimize it. We've tried to reproduce these results of actually having tried to spit out JSON or something that's easily more parsable by a tool. But the plain text one actually worked better because there's just more information on that. Of course, the trick is going to be, what is this context information? In this work here, they try to do a summarization of the queries without giving them the raw SQL. Say, this is my join order or join patterns look like. I have this many cores and so forth, right? And they basically run an integer linear programming problem to figure out what joins should they tell the LLM, because the prompt can only be so big. So if we go back now to the graph we've been showing before of all the different approaches to the problem, well, if we add in the LLM-based approach, we get this. All right? Well, that's kind of disappointing, right? So I think this was using GPT 4.0. It does worse. We use 0.3 mini, right? In this case here, they're only tuning the knobs. They're only tuning the indexes. So they can't tune queries because you can't fit that into the prompt. And when we've tried out using LLMs to give us hints and things like that, we could then feed into Postgres. You still don't get that full benefit that we can get with the specialized algorithm like ProtoX. So what am I missing here? What's the one metric other than performance that I'm not including in my results here? Time, right? So my specialized algorithm that we developed at CMU, I can generate that amazing result in roughly 12 hours. With ChatGPT, it can spit out a pretty good configuration in 14 minutes, for a couple dollars, if that, right? So there is still a huge benefit, because if I say I can get a good result in 14 minutes for fraction of the price, that most people are gonna choose that. The problem I have though with these results is I don't know if I can trust them, because I'm running on this joint order benchmark. It's a well-known benchmark. It's been around for 10 years. Basically, every academic paper is using it. Right? There's a bunch of blog articles, a Stack Exchange post on how to make these queries go fast. So is it really understanding what the database is doing, or does this know how to regurgitate how to make this one benchmark go really, really fast? All right, so how can we get past that? So if you try to obfuscate the query, basically change the table names, change some aspect of the query for any of these well-known benchmarks, turns out the models can still identify what benchmark it actually is. So this is the query from the joint owner benchmark, right? It has it's based on IMDb, the Internet Movie Database, right? So it has a well-known table names, well-known patterns in the queries. So if you try to then obfuscate it, rewrite it, change all the lookups on constants, right? Going back here quickly, right? So we have where country code equals DE for Germany, right? So there's a constant string in there. So it sees that and knows pretty quickly what's going on. So if you replace that with a UDF, so it can't see what the string you're trying to pass in. Even then with this, both ChatGPT, Gemini, Claude, pick your favorite one, can tell you right away that it's going to be, that it's actually what workload it came from, even though we try to hide its origin. So if we actually go now to a demo with Claude, right? So this is me putting in the obfuscated query, and it's going to crunch on for a bit, but it said it can't definitively tell that it's from the joint owner benchmark, but it thinks it is. And then the recommendations going to spit out are going to be for the obfuscated table names, but it's basically going to be the exact same thing that you would get if you gave it the original query. So there's LLM stuff people are doing. Without running on real workloads yet, I can't definitively say I think it's a good idea. And certainly, if you try to have it rewrite SQL, the problem is going to be it's going to end up hallucinating. So the idea, again, you take a SQL query, you throw it to the LLM, say, hey, make this run faster for me, and then it's going to then try to reorder things in the operations, change some casting calls and things like that, things that the query optimizers should be able to fix, they just don't. It's going to generate a new SQL query that it hopes is going to run faster. The challenge is, and in our own experiments, they often are correct in terms of they do run faster, but the new query that they're generating is not semantically the same as the original query. I mean, it's not going to produce the same result. And so now you have this problem where you have a SQL string in a high-level language with a new SQL string in a high-level language. You need a way to figure out whether they're equivalent, and the LLMs aren't good at that at all. There is work in using verification tools, mostly from Alvin Chung at Berkeley, where you kind of do more formal semantics and understanding of what the query is actually trying to do to identify that they're equivalent. But it can't handle, his tools can't handle everything. If you have CTEs, it doesn't work. If you have really nasty nested queries, it doesn't work. So this is still up in the air, but I'd be very skeptical of any tool that's out today that say they can rewrite queries without understanding how they're actually going to verify they're the same. All right, the last one I'm going to show you is something that we've been working on for a while now of trying to solve this problem when we talk about lifecycle management of people upgrading a database. Right, so Postgres puts out a new version a major version of the system once a year. And so the problem is people kind of just run with whatever version of Postgres they had when they created the application. So there's this blog article from the Neon guys where they look at why people are still running these old versions of Postgres. So we try to come up with a tool that can advise people to say, hey, if you upgrade your version of Postgres or whatever database you want, here's what you'll expect. If these queries go faster, these queries go slower, you'll see these kind of benefits or these kind of issues, right? So the way we figured to do this was that we were going to fine-tune an LLM based on Postgres mailing list emails. So this is where people actually post regressions when they upgrade Postgres and they have issues. Like they're going right to the developers and say, here's the problem that I have. Right? So it was a great source to get this information. The problem is that the model became good, but it kind of sucked in the, how to say this, the tone of the mailing list, and it basically became an asshole, like an old man complaining about people posting the mailing list. So this is a little demo. I hope you guys can see it. But we're basically going to bring up the LLM that we fine-tuned, and then we're going to say, hey, if we upgrade to Postgres 15, what's going to happen, right? So it says, oh, you should be so lucky. It's a stupid question, but people are going to ask anyway, right? This is the more cleaner one I've seen that it generates. It can get pretty bad pretty quickly. The problem also, too, is that there's famous Postgres developers like Tom Lane, Bruce Mojim. So it'll start saying asshole things and then attributing it to these Postgres developers, which I don't think are bad people. So this is not something we released in the public because we don't want to piss people off. So it's still up in the air whether LLMs could do this. We're actually pursuing a different approach that isn't using LLMs. That relies on sort of more traditional AI machine learning techniques, and those results have been promising. All right, so what do I think the future looks like? So the LLMs are super fascinating because, again, what are they essentially doing? They're learning from prior knowledge. They're learning from this huge corpus of information that's available on the internet. But the problem is that there's a lot of stuff in there that we don't actually need for databases, right? I don't need it to replicate chapters from Chaucer or recite the Gettysburg Address, but that's in the LLMs, right? I only care about database stuff. The other challenge, too, is that when people post these Stack Exchange comments or post things on mailing lists, you're not getting the full context of what's going on inside the database system when you're asking these, you're asking for help to optimize things. So there's more telemetry, more information we can provide that we then have to figure out how to get that into the LLMs. So I think the future is going to be a combination of using LLMs for what I'll call the reasoning about what to do. Okay, this is what the agentic AI stuff is trying to build, and then it knows about these other tools that could be in its tool chest to optimize specific things. And one of the ways we've been looking at this is actually we can use LLMs to bridge that gap from specialized models that we train for one database instance that then allow us to transfer that knowledge to other database instances so we can sort of bootstrap models more quickly. And this has surprisingly worked really well. The LLMs are doing a fantastic job of taking information, saying on a 10-core box, and then transferring that over to like a 20-core box, or from Postgres 14 and then reapplying to Postgres 15 or 16, right? So we developed a technique. It still hasn't been published yet, so this is an early preview. But again, the idea is that before you run one of these specialized algorithms, you could take training data you've collected from other databases, use the LLM to sort of bootstrap it, and then transfer it over to the next database, and you end up not only produce results or optimizations much faster than you would without doing this, it actually does a better job. So this is take the Unitune, the multi-round tuner, our latest algorithms in the middle, and then the Lambda tune is the one from Cornell using ChatGPT. If we run this sort of boosting agent that we've developed that runs off Llama, so an LLM, you run that first, then produce whatever that is, the configuration that you pass as the input to these other algorithms, you actually do better and in less time. So I don't need 12 hours to compute the best result that I had before. I can get a better result and in a fraction of the time. So where I like this to eventually go is it'd be really nice if there's a foundation model designed just for database systems. You're starting to see people propose foundation models for physics and other specialized domains. There was a paper from Google earlier this year that says, hey, wouldn't it be great if we had a foundation model just on how to tune database systems, right? Again, the idea is a mixture of experts. You're relying on different components to then feed into the different models, right? I don't want to go into the details of it, but this would be fantastic because this means we wouldn't have to have these super large LLM models that have everything that's on the internet inside them. We can have more specialized ones just for anything you want in a database system. The problem is that it's going to be very expensive to collect and very expensive to train. Google, is this being recorded? Okay. Let's just say Google may not be doing this uh, because they may not be able to get the TPUs or GPUs they have to do this. And even if they still end up doing it, they're never going to open source it, which is a shame. So this would be the goal, but it's going to take a while to get there. All right, let me finish up. I'm going to say as I said, except for that upgrade tool that I talked about, none of these things really deal with these long-term lifecycle management issues, right? Because it's hard to do that in these sort of specialized algorithms because it's sort of looking at the database at one snapshot in time and not thinking about the long-term issues that someone might have trying to run a system. So the way to think about this is that there's no notion of time in these systems. You can try to tell the LLM, hey, I'm going to have to do this in a month or so, but it doesn't know how long it takes to build an index. It doesn't know how long it takes to do other things. It doesn't know what the sort of higher level external costs may be involved in running a database for a business. Like I have to run reporting at this date at this day at the end of every month. All that becomes a big challenge. So this is something that we've been working on now, and this is where we think the automated database tuning can go next. And I'm not ready to publicly talk about this yet, but we do have a new startup that we're hope to announce early next year called So You Don't Have To. And the basic idea is that we're going to use the LLM as an agent to then call out to these different optimization algorithms that we developed, where you can give it information about how urgent is some kind of task. Like if my database is on fire, I maybe don't want to run my algorithm that takes 12 hours. I want to run something that's more lightweight, like pgtune or something. And so then you can start understanding how databases are related to each other in your entire organization to understand what happens in prod or what happens in staging, how things get moved from one level to the next. So the name of the company is So You Don't Have To. We tried to name the company So You Don't Have To incorporate it with a SQL injection attack in it. The IRS in the state of Delaware did not like that. So the legal name is SYDHT DTC, where DTC stands for drop table companies. And like I said, the IRS did not like that, but our lawyer was like, "Hey, do you want us to fight this?" I'm like, "No, that sounds expensive. We're not going to do that, right?" But so this is something we hope to put out later in the year. But again, this is where, not just in databases, this is where this agentic stuff is going to go. It's not going to be relying on LLMs to do everything, but it's in conjunction with other tools that are more domain specific that I think are fascinating. Okay, so hopefully I've been able to convey to you today that tuning a database holistically, like for all the aspects of the system at the same time, is a better way of doing this than trying to do this one at a time. And of course, if you can reuse the prior experience we've seen in tuning other databases to tune new databases in the future, then that can make a big difference in performance. And LLMs are essentially doing that, but it's like a shotgun approach because it's trying to suck in everything. And I think the right way to do it going forward would be something that's more narrowly focused. Okay, with that, happy to answer any questions, and thanks for having me.
The kinds of algorithms that you're running here, the optimizations, a human could have come up with these, but you're just making a machine do this work, right? It's not coming up with novel optimizations that a human would have been able to figure out, right?
All right, so his question is like, does our algorithm generate optimizations that a human would not normally figure out? So, because now I can't click. Yeah, sorry, I have a slide on this, but I don't have it. So one of the things that we're able to do in our new algorithm is try out additional, these are very Postgres specific, but try out different configurations with additional parameters attached to them. So for example, when you create an index, you can call create index on column A or column B. In a bunch of database systems, you can actually have what are called include columns. So you say create an index on A, include B. B goes in the leaf nodes, and it's not part of the indexing key. So this is this feature's been around for a long time. It's in the SQL standard, but when we look at real database deployments, nobody uses it because nobody knows how to use it, or maybe not even know it exists. So to your point of like, we haven't seen the machine learning models generate things like, hey, this is fucking crazy. Like, why would anyone do this? Like when the Go guys built their the AlphaGo stuff, it was doing moves that no human would ever do, but it turns out that was actually the right move. We haven't seen that yet, where it tries some funky configuration. Like, there's no reason why you would want to do this. I just don't know whether we've done enough an exhaustive search to explore that entire solution space. Again, in the case of Go, it's there's only one choice, like where to place the stone at every round. In a database system, there's all these multifaceted choices you could have. We haven't been able to see it do things that like seem super bizarre. So one of the things that we can do is we can tune things that people don't normally do.
Has any testing been done with quantum algorithms?
Say it again. Have any
Testing been done with like quantum instead of
like quantum computing?
correct?
Uh, yeah, so this is not my area. So his question is like, are people trying to use quantum algorithms to optimize data systems? Yes, this is very, very, very much like bleeding edge research. The uh, there are a few papers on. And this is not my own research. Actually, the guy at Cornell is doing this kind of stuff as well. There are there are attempts to do index tuning with quantum algorithms. There's attempts to do multi-query optimization with quantum algorithms. So the idea of like trying to instead of optimizing one database system, or sorry, for one query, if I say here's 10 queries that I'm going to run together, generate with optimal plans for that, and that turns out to be sort of fit nicely into what the quantum stuff can do. Um, there's nothing magic about quantum computing, right? The real ones don't exist yet. They're all simulated annealing kind of stuff. So I think it's interesting, but I don't think it, it remains to be seen whether it could be solved. But the startup time for those things are like super high. Like, 'cause you have to like load the thing in. I think it's worse than FPGA. I might be wrong about that. So getting the information into those systems is pretty challenging, and the scale in which you can look at the problem is actually quite limited. So, like for example, it's basically like one hot encoding within a small embedding.
So you would basically have to limit the scope to even study it.
The statement is, would you have to limit the problem to scope to the problem to study it? That's yes, but that's not specific to databases. That's everybody doing quantum computing research right now, right? It's not my area, but this is my understanding.
Yeah, thank you.
Yep. Over here.
I see the aging boosting can be used on other vertical field. Do you have any research beyond the database optimization?
Okay, this question is, agent boosting would be useful for solving other optimization problems. Am I aware of anybody doing this outside of databases? No, because I only care about one thing: databases. Right? It's the most important thing. It's why we're all here. No, I'm not trying to be glib, but like there is. There's a paper from Google called Wapeltinger from like 2016 that sort of had this initial work before BERT that could try to again reason about the similarity of tasks and to limit the search space. I know people applied it to Go and other things, but at the end of the day, all I care about is databases. Yeah, it's the most important thing in life. Everything's a database problem. In the back, yes. If you shout it, I'll repeat it.
There's only about 100,000 LLMs to choose from, right?
Yes.
How do you shortlist the ones that you think that you're going to perform best with? Like, not all of them are going to do SQL the same. So how did you shortlist which ones, and how did you finalize the LLM that you just finally chose to use?
Right. The question is, how do we decide to use these LLMs? Hacker News, man. Whatever shows up on the top of there. So no, in all honesty, like ChatGPT is the leading one. We use that. I'd be honest, the students are guiding a lot of these kind of decisions because it's whatever they end up using. So we haven't played with DeepSeek. We've used Claude. We use ChatGPT. But when we want to run stuff locally, we've had pretty good luck with Llama. Like even Llama 3.2 does pretty well. We haven't played so much with Mistral stuff. Oh, the Quen one, or I forget how to say it, the one from Alibaba, QWEN, that one looks pretty promising as well. I don't have a slide on this, but we did a sweep across different model sizes, and then also the transformer size. I showed Voyage 3. We tried it with other ones. Larger is better, right? It's not a surprise.
Hi.
Yes.
So you mentioned rewriting the queries is pretty hard.
Yes.
It's hard to verify.
Yes.
But currently, the AI writing code is relatively mature. So anything we can borrow from there?
All right. So the question is, AI is really good. LLMs are really good at generating code. Is there anything we can use from them to improve the accuracy of the SQL rewriting? So as I said, I think the latest study shows that like 95% of the SQL that the LLMs generate when you ask to rewrite stuff is actually syntactically correct SQL for whatever target database system you want. That's not the issue, right? You can run that in the parser, for nothing and see that it validates that it's correct SQL syntax. It's the higher level semantics that are difficult to capture in SQL. SQL has much of problems. It's a lot of good things, a lot of bad things, but a lot of it, there's a lot of ambiguities for certain things. And so the simple things like it'll remove or move, it'll move like an order by clause in the SQL. And then if there's like a limit and a nested query, it is actually going to produce the incorrect result. And if you ask LLMs, at least in the research I've seen, like, hey, are these two things same? The success rate is not high enough when anybody would put that in production without having to do some extra steps to make sure it actually works. So, I mean, a simple thing you could do, and something that we played around with last semester was you take whatever the rewrite in SQL query is, and then you have the LLM generate a sample database that looks like whatever the original one is, and then you just run the query on a bunch of different sample databases and see that the original one and the rewritten one produce the same result, right? That's, again, it doesn't prove that it's correct, but at least if you had a way, maybe one of these verification tools that kind of do something, if you took a multifaceted approach, it may be okay, but there's no guarantee. And you talk to the hedge fund guys, they don't want any of this because they want to make sure that whatever query that they wrote that does the thing they want us to do to make a lot of money, it better be the same on the other one, because if it gets it wrong, they're going to lose millions of dollars. Like, nobody wants to be the guy that like fudges the order and tries to sell $500 million instead of $5 of things. So the trust isn't there yet, but it'll get there. In the front, yes.
Into query equivalence at the plan level?
The question is, have people looked at doing query equivalence at the physical plan level? So again, SQL query, the way the basically works is you take a SQL query, the optimizer or will convert that to a logical plan. Like, I want to read this table. I'm not defining how I want to read it. Just says I want to read it. And the physical plan would say, okay, I'm going to read this table with this index or this sequential scan with these threads. And so his question is, have people looked at doing equivalence of physical plans? The problem with that one is, yeah, I don't know the answer. I'd have to think about that, whether this would actually work. The problem is you could have completely different physical plans. And so basically you're back to the problem. You got to you have to convert that into some kind of representation to understand whether it's actually the same without actually running it. It's like the halting problem. Can you tell me whether this program is gonna stop ever?
Yeah, I mean, MP-complete in general.
Yeah, it's hard. So fuzzing and then some verification tools would be the right way to go. But like, if you have really big queries, like the largest one I'm aware of was 10 megabytes, because there's massive inclauses and things like that. Like that, I've not seen anything that can do queries at that scale to prove that they're correct, both in the verification side or on the verification side.
So going back to the last question, would one validation technique be a data diff between the original query on the table and then the new query on a new version of the database? Is that what you are talking about in terms of validation?
Yes, the question is, what do I mean by validation? So validation itself would be, at a high level, are these two queries equivalent? Semantic equivalent will produce the same result no matter what data you ever give it, right? So you can use formal methods. It's not my research area, but I know enough about it. Like, you can use formal methods that basically have algebraic rules that can understand, okay, what does it mean for this operator or this command to do this thing? And then you then can prove, since you know commutative clause, associativity rules, and so forth, that these things are semantically equivalent. And so what I'm saying is my understanding is the latest research in this area can prove for a certain class of queries that yes, they are equivalent and is accurate. It doesn't handle all possible queries. I know that, again, it might have changed in the last year, but CTEs was the one thing that would screw them up. So if you can't formally prove that no matter what data you ever give this, these two queries produce the same result, the next best thing you could do is generate a little test bed to run the query basically like fuzzing on some random data and then see that they always produce the same result. But even then, you still can't prove it. For some people, that's good enough, but for certain mission-critical applications, that's not sufficient. So then now some humans got to go through and figure out whether they're actually correct or not.